Part 2, Chapter 3 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 3. Recent Solar Eclipses. Part 3. The total eclipse of December 22nd, 1889, held out a prospect, unfortunately not realized, of removing some of the doubts and difficulties that impeded the progress of coronal photography. Messrs. Burnham and Scheiberle secured at Cayenne some excellent impressions, showing enough of the corona to prove its identical character with that depicted in the beginning of the year, but not enough to convey additional information about its terminal forms or innermost structure. Any better result was indeed impossible, the moisture-laden air having cut down the actinic power of the coronal light to 1/4 its previous value. Two English expeditions, organized by the Royal Astronomical Society, fared still worse. Mr. Taylor was stationed on the west coast of Africa, 100 miles south of Luanda. Father Perry chose as the scene of his operations the Salut Islands, off French Guiana. Each was supplied with a reflector constructed by Dr. Common, endowed by its extremely short focal length of 45, combined with an aperture of 20 inches, with a light concentrating force capable, it was hoped, of compelling the very filmiest coronal branches to self-registration. Had things gone well, 2 sets of coronal pictures, absolutely comparable in every respect, and taken at an interval of 2 hours and a half, would have been at the disposal of astronomers. But things went very far from well. Clouds altogether obscured the sun in Africa. They only separated to allow of his shining through a saturated atmosphere in South America. Father Perry's observations were the last heroic effort of a dying man. Stricken with malaria, he crawled to the hospital as soon as the eclipse was over, and expired 5 days later, at sea, on board the Coelho. He was buried at Barbados. And the sacrifice of his life had, after all, purchased no decisive success. Most of the plates exposed by him suffered deterioration from the climate, or from an inevitably delayed development. A drawing from the best of them by Miss Violet Common represented a corona differing from its predecessor of January 1st, chiefly through the oppositely unsymmetrical relations of its parts. Then the western wing had been broader at its base than the eastern. Now the inequality was conspicuously the other way. The next opportunity for retrieving the mischances of the past was offered April 16, 1893. The line of totality charted for that day ran from Chile to Senegambia. American parties appropriated the Andes. Both shores of the Atlantic were in English occupation. French expeditions, led by Deslandres and Bijourdin, took up posts south of Cape Verde. A long totality of more than 4 minutes was favored by serene skies, hence an ample store of photographic data was obtained. Professor Scheiberle of the Lick Observatory took, almost without assistance, at Mina Bronces, a mining station 6,600 feet above the Pacific, 52 negatives, 8 of them with a 40-foot telescope, on a scale of 4½ inches to the solar diameter. Not only the inner corona, but the array of prominences then conspicuous, appeared in them to be composed of fibrous jets and arches, held to be sections of elliptic orbits described by luminous particles about the sun's center. One plate received the impression of a curious object, entangled amidst coronal streamers, and the belief in its cometary nature was ratified by the bestowal of a comet medal in recognition of the discovery. Similar paraloidal forms had nevertheless occasionally been seen to make an integral part of earlier coronas, and it remains extremely doubtful whether Schaeberle's eclipse comet was justly entitled to the character claimed for it. The eclipse of 1893 disclosed a radiated corona such as a year of spot maximum was sure to bring. An unexpected fact about it was, however, ascertained. The coronal has been believed to have much in common with the chromospheric spectrum, it proved on investigation with a large prismatic camera, employed under Sir Norman Lockyer's directions by Mr. Fowler at Fundium, to be absolutely distinct from it. The fundamental green ray had on the West African plates 7 more refrangible associates, but all alike are of unknown origin. They may be due to many substances, or to one. Future research will perhaps decide. We can at present only say that the gaseous emissions of the corona include none from hydrogen, helium, calcium, or any other recognizable terrestrial element. Delandre's attempt to determine the rotation of the corona through opposite displacements, east and west of the interposed moon, of the violet calcium lines supposed to make part of the coronal spectrum, was thus rendered nugatory. Yet it gave an earnest of success by definitely introducing the subject into the constantly lengthened program of eclipse work. There is, however, little prospect of its being treated effectively until the green line is vivified by a fresh access of solar activity. The flight of the moon's shadow was on August 9, 1896, dogged by atrocious weather. It traversed, besides, some of the most inhospitable regions on the earth's surface, and afforded at the best but a brief interval of obscurity. At Novaya Zemlya, however, of all places, the conditions were tolerably favorable, and, as we have seen, the trophy of a flash spectrograph was carried off. Some coronal photographs, moreover, taken by the late Sir George Baden-Powell and by M. Hansky, a member of a Russian party, were marked by features of considerable interest. They made apparent a close connection between coronal outflows and chromospheric jets, cone-shaped beams serving as the sheaths or envelopes of prominences. M. Hansky indeed thought that every streamer had a chromospheric eruption at its base. Further, dark veinings of singular shapes unmistakably interrupted the coronal light, and bordered brilliant prominences, reminding us of certain black lines traced by Swift across the anvil protuberance, August 7, 1869. In type, the corona of 1896 produced that of 1886, as befitted its intermediate position in the solar cycle. The eclipse track on January 22, 1898, crossed the Indian peninsula from Viziadrug on the Malabar coast to Mount Everest in the Himalayas. Not a cloud obstructed the view anywhere, and an unprecedented harvest of photographic records was garnered. The flash spectrum, in its successive phases, appeared on plates taken by Sir Norman Lockyer, Mr. Evershed, Professor Campbell, and others. Professor Turner set on foot a novel mode of research by picturing the corona in the polarized ingredient of its light. Mrs. Maunder practically solved the problem of photographing the faint coronal extensions, one ray on her plates running out to nearly 6 diameters from the moon's limb. Yet she used a Dallmeyer lens of only 1½ inches aperture. Her success accorded perfectly with Professor Wadsworth's conclusion that effectiveness in delineation by slight contrasts of luminosity varies inversely with aperture. Triple-coated plates and a comparatively long exposure of 20 seconds contributed to a result unlikely for some time to be surpassed. The corona of 1898 presented a mixed aspect. The polar plumes due at minimum were combined in it with the quadrilateral ogives belonging to spot maxima. A slow course of transformation, in fact, seemed in progress, and it was found to be completed in 1900, when the eclipse of May 28th revealed the typical halo of a quiescent sun. The obscurity on this occasion was short, less than 100 seconds, but was well observed east and west of the Atlantic. No striking gain in knowledge, however, resulted. Important experiments were indeed made on the heat of the corona with Langley's bolometer, but their upshot can scarcely be admitted as decisive. They indicated a marked deficiency of thermal radiations, implying for coronal light, in Professor Langley's opinion, an origin analogous to that of the electric glow discharge, which at low pressures was found by K. Ångström in 1893 to have no invisible heat spectrum. The corona was photographed by Professor Barnard at Wadesboro, North Carolina, with a 61.5-foot horizontal celiostat. In this instrument, of a type now much employed in eclipse operations and first recommended by Professor Turner, a 6-inch photographic objective preserved an invariable position, while a silvered plane mirror, revolving by clockwork once in 48 hours, since the angle of movement is doubled by reflection, supplied the light it brought to a focus. A temporary wooden tube connected the lens with the photographic house where the plates were exposed. Pictures thus obtained with exposures of from 1 to 14 seconds were described as remarkably sharp and perfectly defined, showing the prominences and inner corona very beautifully. The polar fans came out magnificently. The great Sumatra eclipse left behind it manifold memories of foiled expectations. A totality of above 6 minutes drew observers to the Far East from several continents, each cherishing a plan of inquiry, which few were destined to execute. All along the line of shadow, which on May 18, 1901, crossed Réunion and Mauritius, and again met land at Sumatra and Borneo, the meteorological forecast was dubious, and the meteorological actuality in the main deplorable. Nevertheless, the corona was seen and fairly well photographed through drifting clouds, and proved to resemble in essentials the appendage viewed a year previously. Negatives taken by members of the Lick Observatory expedition led by Mr. Perrine disclosed the unique phenomenon of a violent coronal disturbance with a small compact prominence as its apparent focus, tumbling masses and irregular streamers radiating from a point subsequently shown by the Greenwich photographs to be the seat of a conspicuous spot, suggested the recent occurrence of an explosion, the far-reaching effects of which might be traced in the confused floccular luminosity of a vast surrounding region. Again, photographs in polarized light attested the radiance of the outer corona to be in large measure reflected, while that of the inner ring was original, and the inference was confirmed by spectrographs, recording many Fraunhofer lines when the slit lay far from the sun's limb, but none in its immediate vicinity. On plates exposed by Mr. Dyson and Dr. Humphreys with special apparatus, the coronal spectrum, continuous and linear, impressed itself more extensively in the ultraviolet than on any previous occasion, and Dr. Mitchell succeeded in photographing the reversing layer by means of a grating spectroscope. Finally, Mrs. Maunder, at Mauritius, despite mischievous atmospheric tremors, obtained with the Newbegin telescope an excellent series of coronal pictures. The principles of explanation applied to the corona may be briefly described as eruptive and electrical. The first was adopted by Professor Scheiberle in his mechanical theory, advanced in 1890. According to this view, the eclipse halo consists of streams of matter shot out with great velocity from the spot zones by forces acting perpendicularly to the sun's surface. The component particles return to the sun after describing sections of extremely elongated ellipses, unless their initial speed happen to equal or exceed the critical rate of 383 miles a second, in which case they are finally driven off into space. The perspective overlapping and interlacing of these incandescent outflows was supposed to occasion the intricacies of texture visible in the corona, and it should be recorded that a virtually identical conclusion was reached by Mr. Perrine in 1901, by a different train of reasoning, based upon a distinct set of facts. A theory on very much the same lines was, moreover, worked out by M. Bélopolsky in 1897. Scheiberle, however, had the merit of making the first adequate effort to deduce the real shape of the corona as it exists in 3 dimensions from its projection upon the surface of the sphere. A theory on very much the same lines was, moreover, worked out by M. Bélopolsky in 1897. Scheiberle, however, had the merit of making the first adequate effort to deduce the real shape of the corona as it exists in 3 dimensions from its projection upon the surface of the sphere. He failed, indeed, to account for the variation in coronal types by the changes in our situation with regard to the sun's equator. It is only necessary to remark that, if this were so, they should be subject to an annual periodicity, of which no trace can be discerned. Electromagnetic theories have the charm and the drawback of dealing largely with the unknown, but they are gradually losing the vague and intangible character which long clung to them, and the improved definition of their outlines has not, so far, brought them into disaccord with truth. The most promising hypothesis of this kind is due to Professor Bigelow of Washington. His able discussion of the eclipse photographs of January 1, 1889, showed a striking agreement between the observed coronal forms and the calculated effects of a repulsive influence obeying the laws of electric potential, also postulated by Huggins in 1885. Finally, subdivided matter, expelled from the sun along lines of force emanating from the neighborhood of his poles, thus tends to accumulate at equipotential surfaces. In deference, however, to a doubt more strongly felt then than now whether the presence of free electricity is compatible with the solar temperature, he avoided any express assertion that the coronal structure is an electrical phenomenon, merely pointing out that, if it were, its details would be just what they are. Later, in 1892, Pupin in America and Ebert in Germany imitated the coronal streamers by means of electrical discharges in low vacua between small conducting bodies and strips of tinfoil placed on the outside of the containing glass receptacles. Finally, a critical experiment made by Ebert in 1895 served, as Bigelow justly said, to clear up the entire subject and put the theory on a working basis. Having obtained coronoidal effects in the manner described, he proceeded to subject them to the action of a strong magnetic field, with the result of marshalling the scattered rays into a methodical and highly suggestive array. They followed the direction of the magnetic lines of force, and, forsaking the polar collar of the magnetized sphere, surrounded it like a ruffle. The obvious analogy with the aurora polaris and the solar corona was insisted upon by Ebert himself, and has been further developed by Bigelow. According to a recent modification of his hypothesis, the latter appendage is controlled by 2 opposing systems of forces, the magnetic causing the rays to diverge from the poles toward the equator, and the electrostatic urging their spread, through the mutual repulsion of the particles accumulated in the wings, from the equator towards either pole. The cyclical change in the corona, he adds, is probably due to a variation in the balance of power thus established, the magnetic polar influence dominating at minima, the electrostatic at maxima, and he may feel well encouraged by the fortunate combination of many experimental details into one explanatory whole, no less than by the hopeful prospect of further developments, both practical and theoretical, along the same lines. What we really know about the corona can be summed up in a few words. It is certainly not a solar atmosphere. It does not gravitate upon the sun's surface and share his rotation, as our air gravitates upon and shares the rotation of the Earth, and this for the simple reason that there is no visible growth of pressure downward, of which the spectroscope would infallibly give notice, in its gaseous constituents, whereas under the sole influence of the sun's attractive power their density should be multiplied many million times in descent through a mere fraction of their actual depth. They are apparently in a perpetual state of efflux from and influx to our great luminary, under the stress of opposing forces. It is not unlikely that some part at least of the coronal materials are provided by eruptions from the body of the sun. It is almost certain that they are organized and arranged round it through electromagnetic action. This, however, would seem to be influential only upon their white-hot or reflective ingredients, out of which the streamers and aigrettes are composed, since the coronal gases appear, from observations during eclipses, to form a shapeless envelope, with condensations above the spot zones, or at the basis of equatorial extensions. The corona is undoubtedly affected both in shape and constitution by the periodic ebb and flow of solar activity, its low tide form being winged, its high tide formed stellate, while the rays emitted by the gases contained in it fade, and the continuous spectrum brightens at times of minimum sunspots. The appendage as a whole must be of inconceivable tenuity, since comets cut their way through it without experiencing sensible retardation. Not even Sir William Crookes' vacua can give an idea of the rarefaction which this fact implies. Yet the observed luminous effects may not in reality bear witness contradictory of it. One solitary molecule in each cubic inch of space might, in Professor Young's opinion, produce them, while in the same volume of ordinary air at sea level the molecules number, according to Dr. Johnstone Stoney, 20,000 trillions. The most important lesson, however, derived from eclipses is that of partial independence of them. Some of the fruits in the daily study of prominences the next chapter will collect, and the harvest has been rendered more abundant, as well as more valuable, since it has been found possible to enlist, in this department too, the versatile aid of the camera. End of Chapter 3. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Part 2, Chapter 4 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Part 2, Chapter 4, Solar Spectroscopy, Part 1. The new way struck out by Janssen and Lockyer was at once and eagerly followed. In every part of Europe, as well as in North America, observers devoted themselves to the daily study of the chromosphere and prominences. Foremost among these were Lockyer in England, Zollner at Leipzig, Sporer at Anclam, Young at Hanover, New Hampshire, Secchi and Respighi at Rome. There were many others, but these names stood out conspicuously. The first point to be cleared up was that of chemical composition. Leisurely measurements verified the presence above the sun's surface of hydrogen in prodigious volumes, but showed that sodium had nothing to do with the orange-yellow ray identified with it in the haste of the eclipse. From its vicinity to the D pair, than which it is slightly more refrangible, the prominence line was, however, designated D3, and the unknown substance emitting it was named by Lockyer helium. Its terrestrial discovery ensued after 26 years. In March 1895, Professor Ramsay obtained from the rare mineral cleveite a volatile gas, the spectrum of which was found to include the yellow prominence ray. Helium was actually at hand and available for examination. The identification cleared up many obscurities in the chromospheric chemistry. Several bright lines, persistently seen at the edge of the sun and early suspected by Young to emanate from the same source as D3, were now derived from helium in the laboratory, and all the complex emissions of that exotic substance ranged themselves into 6 sets or series, the members of which are mutually connected by numerical relations of a definite and simple kind. Helium is of rather more than twice the density of hydrogen and has no chemical affinities. In almost evanescent quantities it lurks in the Earth's crust and is diffused through the Earth's atmosphere. The importance of the part played in the prominence spectrum by the violet line of calcium was noted by Professor Young in 1872, but since H and K lie near the limit of the visible spectrum, photography was needed for a thorough investigation of their appearances. Aided by its resources, Professor George E. Hale, then at the beginning of his career, detected in 1889 their unfailing and conspicuous presence. The substance emitting them not only constitutes a fundamental ingredient of the chromosphere, but rises, in the fantastic jets thence issuing, to greater heights than hydrogen itself. The isolation of H and K in the solar prominences from any other of the lines usually distinctive of calcium was experimentally proved by Sir William and Lady Huggins in 1897 to be due to the extreme tenuity of the emitting vapor. Hydrogen, helium, and calcium form, then, the chief and unvarying materials of the solar Sierra and its peaks, but a number of metallic elements make their appearance spasmodically under the influence of disturbances in the layers beneath. In September 1871, Young drew up, at Dartmouth College, a list of 103 lines significant of injections into the chromosphere of iron, titanium, chromium, magnesium, and many other substances, during 2 months' observation in the pure air of Mount Sherman, 8,335 feet high, in the summer of 1872. These telltale lines mounted up to 273, and he believes their number might still be doubled by steady watching. Indeed, both Young and Lockyer have more than once seen the whole field of the spectroscope momentarily inundated with bright rays, as if the reversing layer had been suddenly thrust upwards in the chromosphere, and as quickly allowed to drop back again. The opinion would thus appear to be well grounded that the two form one continuous region, of which the lower parts are habitually occupied by the heaviest vapors, but where orderly arrangement is continually overturned by violent eruptive disturbances. The study of the forms of prominences practically began with Huggins' observation of one through an open slit, February 13, 1869. At first it had been thought possible to examine them only in sections, that is, by admitting mere narrow strips or lines of their various kinds of light, while the actual shape of the objects emitting those lines had been arrived at by such imperfect devices as that of giving to the slit of the spectroscope a vibratory moment rapid enough to enable the eye to retain the impression of one part while others were successively presented to it. It was an immense gain to find that their rays had strength to bear so much of dilution with ordinary light as was involved in opening the spectroscopic shutter wide enough to exhibit the tree-like or horn-like or flame-shaped bodies rising over the sun's rim in their undivided proportions. Several diversely colored images of them are formed in the spectroscope. Each may be seen under a crimson, a yellow, a green, and a deep blue aspect. The crimson, however, built up out of the sea line of hydrogen, is the most intense, and is commonly used for purposes of observation and illustration. Friedrich Zollner was, by a few days, beforehand with Huggins in describing the open slit method, but was somewhat less prompt in applying it. His first survey of a complete prominence, pictured in and not simply intersected by the slit of his spectroscope, was obtained July 1, 1869. Shortly afterwards, the plan was successfully adopted by the whole band of investigators. A difference in kind was very soon perceived to separate these objects into two well-marked classes. Its natural and obvious character was shown by its having struck several observers independently. The distinction of cloud prominences from flame prominences was announced by Lockyer April 27, by Zollner June 2, and by Respighi December 4, 1870. The first description are tranquil and relatively permanent, sometimes enduring without striking change for many days. Certain of the included species mimic terrestrial cloud scenery, now appearing like fleecy cirrus transpenetrated with the red glow of sunset, now like prodigious masses of cumulostratus hanging heavily above the horizon. The solar clouds, however, have the peculiarity of possessing stems. Slender columns can ordinarily be seen to connect the surface of the chromosphere with its outlying portions. Hence the fantastic likeness to forest scenery presented by the long ranges of fiery trunks and foliage occasionally seeming to fringe the sun's limb. But while this mode of structure suggests an actual outpouring of incandescent material, certain facts require a different interpretation. At a distance, and quite apart from the chromosphere, prominences have been perceived, by both Secchi and Young, to form, just as clouds form in a clear sky, condensation being replaced by ignition. Filaments were then thrown out downward towards the chromosphere, and finally the usual appearance of a stemmed prominence was assumed. Still more remarkable was an observation made by Trouvelot at Harvard College Observatory, June 26, 1874. A gigantic comma-shaped prominence, 82,000 miles high, vanished from before his eyes by a withdrawal of light as sudden as the passage of a flash of lightning. The same observer has frequently witnessed a gradual illumination or gradual extinction of such objects, testifying to changes in the thermal or electrical condition of matter already in situ. The first photograph of a prominence, as shown by the spectroscope in daylight, was taken by Professor Young in 1870, but neither his method nor that described by Dr. Braun in 1872 had any practical success. This was reserved to reward the efforts toward the same end of Professor Hale, begun at Harvard College in 1889. They were prosecuted soon afterwards at the Kenworth Observatory, Chicago. The great difficulty was to extricate the colored image of the gaseous structure, spectroscopically visible at the sun's limb, from the encompassing glare, a very little of which goes a long way in fogging sensitive plates. To counteract its mischievous effects, a second slit, besides the usual narrow one in front of the collimator, was placed on guard, as it were, behind the dispersing apparatus, so as to shut out from the sensitized surface all light save that of the required quality, the sun's image being allowed to drift across the outer slit, while the plate holder was kept moving at the same rate. The successive sectional impressions thus rapidly obtained finally built up a complete picture of the prominence. Another expedient was soon afterwards contrived. The H and K rays of calcium are always, as we have seen, bright in the spectrum of prominences. They are besides fine and sharp, while the corresponding absorption lines in the ordinary solar spectrum are wide and diffuse. Hence, prominences formed by the spectroscope out of these particular qualities of violet light can be photographed entire and at once, for the simple reason that they are projected upon a naturally darkened background. Atmospheric glare is abolished by local absorption. This beautiful method was first realized by Professor Hale in June, 1891. A spectroheliograph, consisting of a spectroscopic and photographic apparatus of special type attached to the eye end of an equatorial 12 inches in aperture, was erected at Kenwood in March, 1891, and with its aid Professor Hale entered upon original researches of high promise for the advancement of solar physics. Noteworthy above all is his achievement of photographing both prominences and faculæ on the very surface of the sun. The latter had, until then, been very imperfectly observed. They were only visible, in fact, when relieved by their brilliance against the dusky edge of the solar disk. Their convenient emission of calcium light, however, makes it possible to photograph them in all positions and emphasizes their close relationship to prominences. The simultaneous picturing, moreover, of the entire chromospheric ring, with whatever trees or fountains of fire chance to be at the moment issuing from it, has been accomplished by a very simple device. The disk of the sun itself having been screened with a circular metallic diaphragm, it is only necessary to cause the slit to traverse the virtually eclipsed luminary, in order to get an impression of the whole round of its fringing appendages. And the record can be extended to the disk by removing the screen, and carrying the slit back at a quicker rate, when an image of the sun's surface, with the faculae and spots, is formed on the plate exactly within the image of the chromosphere formed during the first exposure. The whole operation, Professor Hale continues, is completed in less than a minute, and the resulting photographs give the first true pictures of the sun, showing all the various phenomena at its surface. Most of these novel researches were, by a remarkable coincidence, pursued independently and contemporaneously by M. Deslandres of the Paris Observatory. The ultraviolet prominence spectrum was photographed for the first time from an uneclipsed sun in June 1891 at Chicago. Besides H and K, 4 members of the Huggins series of hydrogen lines imprinted themselves on the plate. Meanwhile, M. Deslandres was enabled, by fitting quartz lenses to his spectroscope and substituting a reflecting for a refracting telescope, to get rid of the obstructive action of glass upon the shorter light waves, and thus to widen the scope of his inquiry into the peculiarities of those derived from prominences. As the result, not only all the 9 white star lines were photographed from a brilliant sun flame, but 5 additional ones were found to continue the series upward. The wavelengths of these last had, moreover, been calculated beforehand with singular exactness, from a simple formula known as Balmer's law. The new lines accordingly filled places in a manner already prepared for them, and were thus unmistakably associated with the hydrogen spectrum. This is now known to be represented in prominences by 27 lines, forming a kind of harmonic progression, only 4 of which are visibly darkened in the Fraunhofer spectrum of the sun. The chemistry of cloud prominences is simple. Hydrogen, helium, and calcium are their chief constituents. Flame prominences, on the other hand, show, in addition, the characteristic rays of a number of metals, among which iron, titanium, barium, strontium, sodium, and magnesium are conspicuous. They are intensely brilliant, sharply defined in their varying forms of jets, spikes, fountains, waterspouts, of rapid formation and speedy dissolution, seldom attaining to the vast dimensions of the more tranquil kind. Eruptive or explosive by origin, they occur in close connection with spots. Whether casually, the materials ejected as flames, settling and cooling down as dark, depressed patches of increased absorption, or consequently, as a reactive effect of falls of solidified substances from great heights in the solar atmosphere. The 2 classes of phenomena, at any rate, stand in a most intimate relation. They obey the same law of periodicity, and are confined to the same portions of the sun's surface, while quiescent prominences may be found right up to the poles and close to the equator. The general distribution of prominences, including both genera, follows that of faculae much more closely than that of spots. From Father Secchi's and Professor Respighi's observations, 1869–71, were derived the first clear ideas on the subject, which have been supplemented and modified by the later researches of Professors Tacchini and Rico at Rome and Palermo. The results are somewhat complicated, but may be stated broadly as follows. The district of greatest prominence frequency covers and overlaps by several degrees that of the greatest spot frequency. That is to say, it extends to about 40 degrees north and south of the equator. There is a visible tendency to a second pair of maxima nearer the poles. The poles themselves, as well as the equator, are regions of minimum occurrence. Distribution in time is governed by the spot cycle, but the maximum lasts longer for prominences than for spots. The structure of the chromosphere was investigated in 1869 and subsequent years by Professor Respighi, director of the Capitoline Observatory, as well as by Sporer and Brédikhine of the Moscow Observatory. They found this supposed solar envelope to be of the same eruptive nature as the vast protrusions from it, and to be made up of a congeries of minute flames, set close together like blades of grass. The appearance, Professor Young writes, which probably indicates a fact, is as if countless jets of heated gas were issuing through vents and spiracles over the whole surface, thus clothing it with flame, which heaves and tosses like the blaze of a conflagration. The summits of these filaments of fire are commonly inclined, as if by a wind sweeping over them, when the sun's activity is near its height, but erect during his phase of tranquillity. Sporer, in 1871, inferred the influence of permanent polar currents, but Tacchini showed in 1876 that the deflections upon which this inference was based ceased to be visible as the spot minimum drew near. Another peculiarity of the chromosphere, denoting the remoteness of its character from that of a true atmosphere, is the irregularity of its distribution over the sun's surface. There are no signs of its bulging out at the equator, as the laws of fluid equilibrium in a rotating mass would require, but there are some that the fluctuations in its depth are connected with the phases of solar agitation. At times of minimum, it seems to accumulate and concentrate its activity at the poles, while the maxima probably bring a more equable general distribution, with local depressions at the base of great prominences and above spots. The low-lying stratum of carbon vapor was, in 1897, detected in the chromosphere by Professor Hale with a grating spectroscope attached to the 40-inch Yerkes refractor. The eclipse photographs of 1893 disclosed to Hartley's examination the presence of gallium, and those taken by Evershed in 1898 were found by Yuval to be crowded with ultraviolet lines of the equally rare metal scandium. The general rule had been laid down by Sir Norman Lockyer that the metallic radiations from the chromosphere were those enhanced in the electric spark. Hence the comparative study of conditions prevalent in the arc and the spark has acquired great importance in solar physics. The reality of the appearance of violent disturbance presented by the flaming kind of prominence can be tested in a very remarkable manner. Christian Doppler, professor of mathematics at Prague, enounced in 1842 the theorem that the color of a luminous body, like the pitch of a sonorous body, must be changed by movements of approach or recession. The reason is this: both color and pitch are physiological effects, depending not upon absolute wavelength, but upon the number of waves entering the eye or ear in a given interval of time, and this number, it is easy to see, must be increased if the source of light or sound is diminishing at distance, and diminished if it is decreasing it. In the one case, the vibrating body pursues and crowds together the waves emanating from it; in the other, it retreats from them, and so lengthens out the space covered by an identical number. The principle may be thus illustrated. Suppose shots to be fired at a target at fixed intervals of time. If the marksman advances, say 20 paces between each discharge of his rifle, it is evident that the shots will fall faster on the target than if he stood still. If, on the contrary, he retires by the same amount, they will strike at correspondingly longer intervals. The result will of course be the same whether the target or the marksman be in movement. So far Doppler was altogether right. As regards sound, anyone can convince himself that the effect he predicted is a real one, by listening to the alternate shrilling and sinking of the steam whistle when an express train rushes through a station. But in applying this principle to the colors of stars, he went widely astray, for he omitted from consideration the double range of invisible vibrations which partake of, and to the eye exactly compensate, changes of refrangibility in the visible rays. There is, then, no possibility of finding a criterion of velocity in the hue of bodies shining, like the sun and stars, with continuous light. The entire spectrum is slightly shifted up or down in the scale of refrangibility, Certain rays normally visible become exalted or degraded, as the case may be, into invisibility, and certain other rays at the opposite end undergo the converse process, but the sum total of impressions on the retina continues the same. We are not, however, without the means of measuring this subsensible transportation of the light gamut. Once more the wonderful Fraunhofer lines came to the rescue. They are called by the earlier physicists fixed lines, but it is just because they are not fixed that in this instance we find them useful. They share, and in sharing betray, the general shift of the spectrum. This aspect of Doppler's principle was adverted to by Fizeau in 1848, and the first tangible results in the estimation of movements of approach and recession between the earth and the stars were communicated by Sir William Huggins to the Royal Society, April 23, 1868. 18 months later, Zollner devised his reversion spectroscope for doubling the measurable effects of line displacements, aided by which ingenious instrument, and following a suggestion of its inventor, Professor H. C. Vogel, succeeded at Bothkamp, June 9, 1871, in detecting effects of that nature due to the solar rotation. This application constitutes at once the test and the triumph of the method. The eastern edge of the sun is continually moving towards us with an equatorial speed of about 1.25 miles per second, the western edge retreating at the same rate. The displacements, toward the violet on the east, towards the red on the west, corresponding to this velocity are very small, so small that it seems hardly credible that they should have been laid bare to perception. They amount to but 1/150th part of the interval between the two constituents of the D line of sodium, and the D line of sodium itself can be separated into a pair only by a powerful spectroscope. Nevertheless, Professor Young was able to show, quite satisfactorily, in 1876, not only deviations in the solar lines from their proper places indicating a velocity of rotation, 1.42 miles per second, slightly in excess of that given by observations of spots, but the exemption of terrestrial lines, those produced by absorption in the Earth's atmosphere, from the general push upwards or downwards. Shortly afterwards, Professor Langley, then director of the Allegheny Observatory, having devised a means of comparing with great accuracy light from different portions of the sun's disk, found while the obscure rays in two juxtaposed spectra derived from the solar poles were absolutely continuous, no sooner was the instrument rotated through 90 degrees, so as to bring its luminous supplies from opposite extremities of the equator, than the same rays became perceptibly notched. The telluric lines meanwhile remained unaffected, so as to become virtually mapped by the process. This rapid and unfailing mode of distinction was used by Cornu with perfect ease during his investigation of atmospheric absorption near Loiret in August and September, 1883. A beautiful experiment of the same kind was performed by M. Thollon of M. Bischofsheim's observatory at Nice in the summer of 1880. He confined his attention to one delicately defined group of 4 lines in the orange, of which the inner part are solar, that is iron, and the outer terrestrial. At the center of the sun the intervals separating them were sensibly equal. But when the light was taken alternately from the right and left limbs, a relative shift in alternate directions of the solar, towards and from the stationary telluric rays, became apparent. A parallel observation was made at Dunnet, December 14, 1883, when it was noticed that a strong iron line in the yellow part of the solar spectrum is permanently double on the sun's eastern, but single on his western limb. Opposite motion displacements bringing about this curious effect of coincidence with and separation from an adjacent stationary line of our own atmosphere's production, according as the spectrum is derived from the retreating or advancing margin of the solar globe. Statements of fact so precise and authoritative amount to a demonstration that results of this kind are worthy of confidence, and they already occupy an important place among astronomical data. The subtle method of which they serve to assure the validity was employed in 1887 to 89 by M. Danner to test and extend Carrington's and Sporer's conclusions as to the anomalous nature of the sun's axial movement. His observations for the purpose, made with a fine diffraction spectroscope just then mounted at the Observatory of Upsala, were published in 1891. Their upshot was to confirm and widen the law of retardation with increasing latitude derived from the progressive motions of spots. Determinations made within 15 degrees of the pole, consequently far beyond the region of spots, gave a rotation period of 38½, that of the equatorial belt being of 25½ days. Spots near the equator, indeed, complete their rounds in a period shorter by at least half a day, and the proportionate differences were found to exist elsewhere in corresponding latitudes. But Dunier's observations, it must be remembered, apply to a distinct part of the complex solar machine from the disturbed photospheric surface. It is amply possible that the absorptive strata producing the Fraunhofer lines, significant, by their varying displacements at either limb, of the inferred varying rates of rotation, may gyrate more slowly than the spot-generating level. Moreover, faculae appear to move at a quicker pace than either, so that we have, for 3 solar formations, 3 different periods of average rotation, the shortest of which belongs to the faculae, one of the intermediate length to the spots, and the most protracted to the reversing layer. All, however, agree in lengthening progressively from the equator towards the poles. Professor Holden aptly compared the sun to a vast whirlpool where the velocities of rotation depend not only on the situation of the rotating masses as to latitude, but also as to depth beneath the exterior surface. Sir Norman Lockyer promptly perceived the applicability of the surprising discovery of line shiftings through end-on motion to the study of prominences, the discontinuous light of which affords precisely the same means of detecting movement without seeming change of place, as do lines of absorption in a continuous spectrum. Indeed, his observations at the sun's edge almost compel recourse to an explanation made available just when the need of it began to be felt. He saw bright lines not merely pushed aside from their normal places by a barely perceptible amount, but bent, torn, broken, as if by the stress of some tremendous violence. These remarkable appearances were quite simply interpreted as the effects of movements varying in amount and direction in the different parts of the extensive mass of incandescent vapors falling within a single field of view. Very commonly they are of a cyclonic character. The opposite distortions of the same colored rays betray the fury of counter gales, rushing along at the rate of 120 miles a second, while their undisturbed sections prove the persistence of a heart of peace in the midst of that unimaginable fiery whirlwind. Velocities up to 250 miles a second, or 15,000 times that of an express train at the top of its speed, were thus observed by Young during his trip to Mount Sherman, August 2, 1872, and these were actually doubled in an extraordinary outburst observed by Father Jules Fenny on June 17, 1891, at the Haynal Observatory in Hungary, as well as by M. Trouvelot at Meudon. Motions ascertainable in this way near the limb are, of course, horizontal as regards the sun's surface. The analogies they present might accordingly be styled meteorological rather than volcanic. But vertical displacements on a scale no less stupendous can also be shown to exist. Observations of the spectra of spots centrally situated, where motions in the line of sight are vertical, disclose the progress of violent uprushes and downrushes of ignited gases, for the most part in the penumbral or outlying districts. They appear to be occasioned by fitful and irregular disturbances, and have none of the systematic quality which would be required for the elucidation of sunspot theories. Indeed, they almost certainly take place at a great height above the actual openings in the photosphere. End of chapter 4, part 1. Part 2, Chapter 4 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 2, Chapter 4, Solar Spectroscopy, Part 2. As to vertical motions above the limb, on the other hand, we have direct visual evidence of a truly amazing kind. The projected glowing matter has, by the aid of the spectroscope, been watched in its ascent. On September 7, 1871, Young examined at noon a vast hydrogen cloud 100,000 miles long, as it showed to the eye, and 54,000 high. It floated tranquilly above the chromosphere at an elevation of some 15,000 miles, and was connected with it by 3 or 4 upright columns, presenting the not uncommon aspect compared by Lockyer to a grove of banyans. Called away for a few minutes at 12:30, on returning at 12:55, the observer found that in the meantime the whole thing had been literally blown to shreds by some inconceivable uprush from beneath. In place of the quiet cloud I had left, the air, if I may use the expression, was filled with flying debris, a mass of detached, vertical, fusiform filaments, each from 10 feet to 30 feet by 2 or 3 feet wide, brighter and closer together where the pillars had formerly stood, and rapidly ascending. They rose, with a velocity estimated at 166 miles a second, to fully 200,000 miles above the sun's surface, then gradually faded away like a dissolving cloud, and at 1:15 only a few filmy wisps, with some brighter streamers low down near the photosphere, remained to mark the place. A velocity projection of at least 500 miles per second was, by Proctor's calculation, required to account for this extraordinary display, to which the earth immediately responded by a magnetic disturbance and a fine aurora. It has proved by no means an isolated occurrence. Young saw its main features repeated October 7, 1881, on a still vaster scale, for the exploded Prominence attained this time an altitude of 350,000 miles, the highest yet chronicled. Lockyer, moreover, has seen a Prominence 40,000 miles high shattered in 10 minutes, while uprushes have been witnessed by Respighi, of which the initial velocities were judged by him to be 400 or 500 miles a second. When it is remembered that a body starting from the sun's surface at the rate of 383 miles a second would, if it encountered no resistance, escape forever from his control, it is obvious that we have, in the enormous forces of eruption or repulsion manifested in the outbursts just described, the means of accounting for the vast diffusion of matter in the solar neighborhood. Nor is it possible to explain them away, as Cornu, Faye, and others have sought to do, by substituting for the rush of matter in motion progressive illumination through electric discharges, chemical processes, or even through the mere reheating of gases cooled by expansion. All the appearances are against such evasions of the difficulty presented by velocities stigmatized as fabulous and improbable, but which, there is the strongest reason to believe, really exist. On the 12th of December, 1878, Sir Norman Lockyer formally expounded before the Royal Society his hypothesis of the compound nature of the chemical elements, a hypothesis, it is true, over and over again propounded from the simply terrestrial point of view. What was novel was the supra-terrestrial evidence adduced in its support, and even this had been, in a general and speculative way, anticipated by Professor F. W. Clerke of Washington. Lockyer had been led to his conclusion along several converging lines of research. In a letter to M. Dumas, dated December 3, 1873, he had sketched out the successive stages of celestial dissociation, which he conceived to be represented in the sun and stars. The absence from the solar spectrum of metalloidal absorption he explained by the separation, in the fierce solar furnace, of such substances as oxygen, nitrogen, sulfur, and chlorine, into simpler constituents possessing unknown spectra, while metals were at that time still admitted to be capable of existing there in a state of integrity. 3 years later he shifted his position onward. He announced, as the result of a comparative study of the Fraunhofer and electric arc spectra of calcium, that the molecular grouping of that metal, which at low temperatures gives a spectrum with its chief line in the blue, is nearly broken up in the sun into another or others with lines in the violet. This came to be regarded by him as a truly typical case. During 4 years, 1875 to 78 inclusive, this diligent observer was engaged in mapping a section of the more refrangible part of the solar spectrum, wavelengths of 3,800 to 4,000, on a scale of magnitude such that, if completed down to the infrared, its length would have been about half a furlong. The attendant laborious investigation, by the aid of photography, of metallic spectra seemed to indicate the existence of what he called basic lines. These held their ground persistently in the spectra of 2 or more metals after all possible impurities had been eliminated, and were therefore held to attest the presence of a common substratum of matter in a simpler state of agitation than any with which we are ordinarily acquainted. Later inquiries have shown, however, that between the spectral lines of different substances there are probably no absolute coincidences. Basic lines are really formed of doublets or triplets merged together by insufficient dispersion. Of Thalin's original list of 70 rays common to several spectra, very few resisted Thollon's and Young's powerful spectroscopes, and the process of resolution was completed by Rowland. Thus the argument from community of lines to community of substance has virtually collapsed. It was replaced by one founded on certain periodical changes on the spectra of sunspots. They emerged from a series of observations begun at South Kensington under Sir Norman Lockyer's direction in 1879 and continued for 15 years. The principle of the method employed is this: the whole range of Fraunhofer lines is visible when the light from a spot is examined with the spectroscope, but relatively few are widened. Now these widened lines alone constitute presumably the true spot spectrum. They and they alone tell what kinds of vapor are thrust down into the strange dusky pit of the nucleus, the unaffected lines taking their accustomed origin from the overlying strata of the normal solar atmosphere. Here, then, we have the criterion that was wanted, the means of distinguishing, spectroscopically and chemically, between the cavity and the absorbing layers piled up above it. By its persistent employment, some marked peculiarities have been brought out, such as the unfamiliar character of numerous lines in spot spectra, especially at epochs of disturbance, and the strange individuality in the behavior of every one of these darkened and distended rays. Each seems to act on its own account. It comports itself as if it were the sole representative of the substance emitting it. Its appearance is unconditioned by that of any of its terrestrial companions in the same spectrum. The most curious fact, however, elicited by these inquiries was that of the attendance of chemical vicissitudes upon the advance of the sunspot period. As the maximum approached, unknown replaced known components of the spot spectra in a most pronounced and unmistakable way. It seemed as if the vapors emitting lines of iron, titanium, nickel, etc., had ceased to exist as such, and their room been taken by others, total strangers in terrestrial laboratories. These were held by Lockyer to be simply the finer constituents of their predecessors, dissociation having been effected by the higher temperature ensuing upon increased solar activity. But Father Cordy's supplementary investigations at Stonyhurst modified, while they in the main substantiated, the South Kensington results. They showed that the substitution of unknown for known lines characterizes disturbed spots at all stages of the solar cycle, so that no systematic course of chemical change can be said to affect the sun as a whole. They showed further, from evidence independent of that obtained by Young in 1892, the remarkable conspicuousness in spot spectra of vanadium lines excessively faint in the Fraunhofer spectrum. Lockyer's unknown lines may probably thus be accounted for. They represent absorption, not by new but by scarce elements, especially, Father Cordy thinks, those with atomic weights of about 50. The circumstance of their development in solar commotions, largely to the exclusion of iron, is none the less curious, but it cannot be explained by any process of dissociation. The theory has, however, to be considered under still another aspect. It frequently happens that the contortions or displacements due to motion are seen to affect a single line belonging to a particular substance, while the other lines of that same substance remain imperturbable. Now how is this most singular fact, which seems at first sight to imply that a body may be at rest and in motion at one and the same instant, to be accounted for? It is accounted for, on the present hypothesis, easily enough, by supposing that the rays thus discrepant in their testimony do not belong to one kind of matter, but to several, combined at ordinary temperatures to form a body in appearance elementary. Of these different vapors, one or more may, of course, be rushing rapidly towards or from the observer, while the others remain still, and since the line of sight across the average prominence region penetrates at the sun's edge a depth of about 300,000 miles, all the incandescent materials separately occurring along which line are projected into a single flame or cloud, it will be perceived that there is ample room for diversities of behavior. The alternative mode of escape from the perplexity consists in assuming that the vapor in motion is rendered luminous under conditions which reduce its spectrum to a few rays, the unaffected lines being derived from a totally distinct mass of the same substance shining with its ordinary emissions. Thus calcium can be rendered virtually monochromatic by attenuation, and analogous cases are not rare. Sir Norman Lockyer only asks us to believe that effects which follow certain causes on the earth are carried a stage farther in the sun, while the same causes must be vastly intensified. We find that the bodies we call compound split asunder at fixed degrees of heat within the range of our resources. Why should we hesitate to admit that the bodies we call simple do likewise at degrees of heat without the range of our resources? The term element simply expresses terrestrial incapability of reduction. That in celestial laboratories the means and their effect here absent should be present would be an inference challenging in itself no expression of incredulity. There are indeed theoretical objections to which, though probably not insuperable, are unquestionably grave. Our 70 chemical elements, for instance, are placed by the law of specific heats on a separate footing from their known compounds. We are not, it is true, compelled by it to believe their atoms to be really and absolutely such, to contain, that is, the irreducible minimum of material substance, but we do certainly gather from it that they are composed on a different principle from the salts and oxides made and unmade at pleasure by chemists. Then the multiplication of the species of matter with which Lockyer's results menace us is at first sight startling. They may lead, we are told, to eventual unification, but the prospect appears remote. Their only obvious outcome is the disruption into several constituents of each terrestrial element. The components of iron alone should be counted by the dozen. And there are other metals, such as cerium, which, giving a still more complex spectrum, would doubtless be still more numerously resolved. Sir Norman Lockyer interprets the observed phenomena as indicating the successive combinations in varying proportions of a very few original ingredients, but no definite sign of their existence is perceptible. Protyle seems long to evade recognition, and the only intelligible underlying principle for the reasonings employed, that of one line, one element, implies a throng beyond counting of formative material units. Thus, added complexity is substituted for that fundamental unity of matter which has long formed the dream of speculators, and it is extremely remarkable that Sir William Crookes, working along totally different lines, has been led to analogous conclusions. To take only one example, as the outcome of extremely delicate operations of sifting and testing carried on for years, he finds that the metal yttrium splits up into 5, if not 8 constituents. Evidently, old notions are doomed, nor are any preconceived ones likely to take their place. It would seem, on the contrary, as if their complete reconstruction were at hand. subversive facts are steadily accumulating. The revolutionary ideas springing from them tend, if we interpret them aright, towards the substitution of electrical for chemical theories of matter. Dissociation by the brute force of heat is already nearly superseded in the thoughts of physicists by the more delicate process of ionization. Precisely what this implies and involves we do not know, but the symptoms of its occurrence are probably altogether different from those gathered by Sir Norman Lockyer from the collation of celestial spectra. A. J. Ångström of Uppsala takes rank after Kirchhoff as a subordinate founder, so to speak, of solar spectroscopy. His great map of the normal solar spectrum was published in 1868, 2 years before he died. Robert Thalen was his coadjutor in its execution, and the immense labor which it cost was amply repaid by its eminent and lasting usefulness. For more than a score of years it held its ground as the universal standard of reference in all spectroscopic inquiries within the range of the visible emanations. Those that are invisible, by reason of the quickness of their vibrations, were mapped by Dr. Henry Draper of New York in 1873, and with superior accuracy by M. Cornu in 1881. The infrared part of the spectrum, investigated by Langley, Abney, and Knut Ångström, reaches perhaps no definite end, the radiations oscillating too slowly to affect the eye, as light may pass by insensible gradations by the long Hertzian waves of electricity. Professor Rowland's photographic map of the solar spectrum, published in 1886, and a second enlarged edition in 1889, opened fresh possibilities for its study, from far down in the red to high up in the ultraviolet, and the accompanying scale of absolute wave lengths has been, with trifling modifications, universally adopted. His new table of standard solar lines was published in 1893. Through his work, indeed, knowledge of the solar spectrum so far outstripped knowledge of terrestrial spectra that the recognition of their common constituents was hampered by intolerable uncertainties. Thousands of solar lines charted with minute precision remained unidentified for want of a corresponding precision in the registration of metallic lines. Rowland himself, however, undertook to provide a remedy. Aided by Louis E. Jewell, he redetermined at Johns Hopkins University the wavelengths of about 16,000 solar lines, photographing for comparison with them the spectra of all known chemical elements except gallium, of which he could procure no specimen. The labor of collation was well advanced when he died at the age of 52, April 16, 1901. Investigations of metallic arc spectra have also been carried out with signal success by Hasselberg, Kayser, and Runge, O. Lohse, and others. Another condition sine qua non of progress in this department is the separation of true solar lines from those produced by absorption in our own atmosphere, and here little remains to be done. Tholen's great atlas was designed for this purpose of discrimination. Each of its 33 maps exhibits, in quadruplet, a subdivision of the solar spectrum under varied conditions of weather and zenith distance. Telluric effects are thus made easily legible, and they account wholly for 866, partly for 246, out of a total of 3,200 lines. But the death of the artist, April 8, 1887, unfortunately interrupted the half-finished task of the last 7 years of his life. A most satisfactory record, meanwhile, of selective atmospheric action has been supplied by the experiments and determinations of Janssen, Cornu, and Egorov, by Dr. Becker's drawings, and Mr. McLean's photographs of the analyzed light of the sun at high, low, and medium altitudes, and the autographic pictures obtained by Mr. George Higgs of Liverpool of certain rhythmical groups in the red, emerging with surprising strength near sunset, excite general and well-deserved admiration. The main interest, however, of all these documents resides in the information afforded by them regarding the chemistry of the sun. The discovery that hydrogen exists in the atmosphere of the sun was made by Ångström in 1862. His list of solar elements published in that year, the result of an investigation separate from, though conducted on the same principle as Kirchhoff's, included the substance which we now know to be predominant among them. Dr. Plücker of Bonn had identified in 1859 the Fraunhofer line F with the green ray of hydrogen, but drew no inference from his observation. The agreement was verified by Ångström, two further coincidences were established, and in 1866 a fourth hydrogen line in the extreme violet, named h, was detected in the solar spectrum. With Thalin, he besides added manganese, titanium, and cobalt to the constituents of the sun enumerated by Kirchhoff, and raised the number of identical rays in the solar and terrestrial spectra of iron to no less than 460. Thus, when Sir Norman Lockyer entered on that branch of inquiry in 1872, 14 substances were recognized as common to the earth and sun. Early in 1878, he was able to increase the list provisionally to 33, all except hydrogen metals. This rapid success was due to his adoption of the test of length in lieu of that of strength in the comparison of lines. He measured their relative significance, in other words, rather by their persistence through a wide range of temperature than by their brilliance at any one temperature. The distinction was easily drawn. Photographs of the electric arc, in which any given metal had been volatilized, showed some of the rays emitted by its stretching across the axis of the light to a considerable distance on either side, while many others clung more or less closely to its central hottest core. The former long lines, regarded as certainly representative, were those primarily sought in the solar spectrum, while the attendant short lines, often, in point of fact, due to foreign admixtures, were set aside as likely to be misleading. The criterion is a valuable one, and its employment has greatly helped to quicken the progress of solar chemistry. Carbon was the first non-metallic element discovered in the sun. Messrs. Trowbridge and Hutchins of Harvard College concluded in 1887, on the ground of certain spectral coincidences, that this protein substance is vaporized in the solar atmosphere at a temperature approximately that of the voltaic arc. Partial evidence to the same effect had earlier been alleged by Lockyer, as well as by Liveling and Dewar, and the case was rendered tolerably complete by photographs taken by Kayser and Runge in 1889. It was by Professor Rowland shown to be irresistible. 200 carbon lines were, through his comparisons, sifted out from sunlight, and it contained others significant of the presence of silicon, a related substance, and one as important to rock building on the earth as carbon is to the maintenance of life. The general result of Rowland's labors was the establishment among solar materials not only of these two out of the 14 metalloids, or non-metallic substances, but of 33 metals, including silver and tin. Gold, mercury, bismuth, antimony, and arsenic were discarded from the catalogue. Platinum and uranium, with 6 other metals, remained doubtful, while iron was recorded as crowding the spectrum with over 2,000 obscure rays. Gallium absorption was detected in it by Hartley and Ramage in 1889. Dr. Henry Draper announced in 1877 his imagined discovery in the solar spectrum of 18 especially brilliant spaces corresponding to oxygen emissions, but the agreement proved, when put to the test of very high dispersion, to be wholly illusory. Nor has it yet been found possible to identify in analyzed sunlight any significant bright beams. The book of solar chemistry must be read in characters exclusively of absorption. Nevertheless, the whole truth is unlikely to be written there. That a substance displays none of its distinctive beams in the spectrum of the sun or of a star affords scarcely a presumption against its presence, for it may be situated below the level where absorption occurs, or under a pressure such as to efface lines by widening and weakening them. It may be at a temperature so high that it gives off more light than it takes up, and yet its incandescence may be masked by the absorption of other bodies. Finally, it may just balance absorption by emission with the result of complete spectral neutrality. An instructive example is that of the chromospheric element helium. Father Secchi remarked in 1868 that there is no dark line in the solar spectrum matching its light, and his observation has been fully confirmed. Helium absorption is, however, occasionally noticed in the penumbrae of spots. Our terrestrial vital element might then easily subsist unrecognizably in the sun. The inner organization of the oxygen molecule is a considerably plastic one. It is readily modified by heat, and these modifications are reflected in its varying modes of radiating light. Dr. Schuster enumerated in 1879 4 distinct oxygen spectra, corresponding to various stages of temperature or phases of electrical excitement, and a fifth has been added by M. Egorof's discovery in 1883 that certain well-known groups of dark lines in the red end of the solar spectrum, Fraunhofer's A and B, are due to absorption by the cool oxygen of our air. These persist down to the lowest temperatures and even survive a change of state. They are produced essentially the same by liquid as by aerial oxygen. It seemed, however, possible to M. Janssen that these bands owned a joint solar and terrestrial origin. Oxygen in a fit condition to produce them might, he considered, exist in the outer atmosphere of the sun, and he resolved to decide the point. No one could bring more skill and experience to bear upon it than he. By observations on the summit of the Faulhorn, as well as by direct experiment, he demonstrated, nearly 30 years ago, the leading part played by water vapor in generating the atmospheric spectrum, and he had recourse to similar means for appraising the share in it assignable to oxygen. An electric beam, transmitted from the Eiffel Tower to Meudon in the summer of 1888, having passed through a weight of oxygen about equal to that piled above the surface of the earth, showed that groups A and B, just as they appear in the high sun spectrum. Atmospheric action is then adequate to produce them. But M. Janssen desired to prove, in addition, that they diminish proportionately to its amount. His ascent of Mont Blanc in 1890 was undertaken with this object. It was perfectly successful. In the solar spectrum, examined from that eminence, oxygen absorption was so much enfeebled as to leave no possible doubt of its purely telluric origin. Under another form, nevertheless, it has been detected as indubitably solar. A triplet of dark lines, low down in the red, photographed from the sun by Higgs and Maclean, was clearly identified by Runge and Paskin in 1896 with the fundamental group of an oxygen series, first seen by Piazzi Smyth in the spectrum of a vacuum tube in 1883. The pabulum vitae of our Earth is then to some slight extent effective in arresting transmitted sunlight, and oxygen must be classed as a solar element. The rays of the sun, besides being stopped selectively in our atmosphere, suffer also a marked general absorption. This tells chiefly upon the slowest wave lengths. The ultraviolet spectrum is in fact closed, if by the interposition of an opaque screen. Nor does the screen appear very sensibly less opaque from an elevation of 10,000 feet. Dr. Simony's spectral photographs, taken on the peak of Teneriffe, extended but slightly further up than M. Cornu's, taken in the valley of the Loire. Could the veil be withdrawn, some indications as to the originating temperature of the solar spectrum might be gathered from its range, since the proportion of quick vibrations given out by a glowing body grows with the intensity of its incandescence, and this brings us to the subject of our next chapter. End of chapter 4, part 2.
Part 2, Chapter 5 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 5, Temperature of the Sun. Newton was the first who attempted to measure the quantity of heat received by the earth from the sun. His object in making the experiment was to ascertain the temperature encountered by the comet of 1680 at its passage through perihelion. He found it by multiplying the observed heating effects of direct sunshine according to the familiar rule of the inverse squares of the distances to be about 2,000 times that of red-hot iron. Determinations of the sun's thermal power, made with some scientific exactness, date, however, from 1837. A few days previous to the beginning of that year, Herschel began observing at the Cape of Good Hope with an actinometer, and obtained results agreeing quite satisfactorily with those derived by Pouillet from experiments made in France some months later with a pyroheliometer. Pouillet found that the vertical rays of the sun falling on each square centimetre of the earth's surface are competent, apart from atmospheric absorption, to raise the temperature of 1.7633 grams of water 1 degree centigrade per minute. This number, 1.7633, he called the solar constant, and the unit of heat chosen is known as the calorie. Hence it was computed that the total amount of solar heat received during a year would suffice to melt a layer of ice covering the entire earth to a depth of 30.89 meters, or 100 feet, while the heat emitted would melt at the sun's surface a stratum 11.80 meters thick each minute. A careful series of observations showed that nearly half the heat incident upon our atmosphere is stopped in its passage through it. Herschel got somewhat larger figures, though he assigned only a third as the spoil of the air. Taking a mean between his own and Pouillet's, he calculated that the ordinary expenditure of the sun per minute would have power to melt a cylinder of ice 184 feet in diameter, reaching from his surface to that of A Centauri; or, putting it otherwise, that an ice rod 45.3 miles across, continually darted into the sun with the velocity of light, would scarcely consume, in dissolving, the thermal supplies now poured abroad into space. It is nearly certain that this estimate should be increased by about two-thirds in order to bring it up to the truth. Nothing would, at first sight, appear simpler than to pass from a knowledge of solar emission, a strictly measurable quantity, to a knowledge of the solar temperature, this being defined as the temperature to which a surface thickly coated with lamp-black, that is, of standard radiating power, should be raised to enable it to send us, from the sun's distance, the amount of heat actually received from the sun. Sir John Herschel showed that heat rays at the sun's surface must be 92,000 times as dense as when they reach the earth, but it by no means follows that either the surface emitting or a body absorbing those heat rays must be 92,000 times hotter than a body exposed here to the full power of the sun. The reason is that the rate of emission, consequently the rate of absorption, which is its correlative, increases very much faster than the temperature. In other words, a body radiates or cools at a continually accelerated pace as it becomes more and more intensely heated above its surroundings. Newton, however, took it for granted that radiation and temperature advance pari passu, that you have only to ascertain the quantity of heat received from and the distance of a remote body in order to know how hot it is; and the validity of this principle, known as Newton's law of cooling, was never questioned until De la Roche pointed out in 1812 that it was approximately true only over a low range of temperature, while 5 years later Dulong and Petit generalized experimental results into the rule that while temperature grows by arithmetical, radiation increases by geometrical progression. Adopting this formula, Pouillet derived from his observations on solar heat a solar temperature of somewhere between 1,461 degrees and 1,761 degrees centigrade. Now the higher of these points, which is nearly that of melting platinum, is undoubtedly surpassed at the focus of certain burning glasses which have been constructed of such power as virtually to bring objects placed there within 250,000 of miles of the photosphere. In the rays thus concentrated, platinum and diamond become rapidly vaporized, notwithstanding the great loss of heat by absorption, first in passing through the air, and again in traversing the lens. Pouillet's maximum is then manifestly too low, since it involves the absurdity of supposing a radiating mass capable of heating a distant body more than it is itself heated. Less demonstrably, but scarcely less surely, Mr. J. J. Waterston, who attacked the problem in 1860, erred in the opposite direction, working up on Newton's principle data collected by himself in India and at Edinburgh. He got for the potential temperature of the sun 12,880,000 degrees Fahrenheit, equivalent to 7,156,000 degrees centigrade. The phrase potential temperature, for which Viol substituted in 1876 effective temperature, was designed to express the accumulation in a single surface, postulated for the sake of simplicity, of the radiations not improbably received from a multitude of separate solar layers reinforcing each other, and might thus, it was explained, be considerably higher than the actual temperature of any one stratum. At Rome in 1861, Father Secchi repeated Waterston's experiments and reaffirmed his conclusion, while Soret's observations made on the summit of Mont Blanc in 1867 furnished him with materials for a fresh and even higher estimate of 10,000,000 degrees centigrade. Yet from the very same data, substituting Dulong and Petit's for Newton's law, Weir deduced in 1872 a provisional solar temperature of 1,398 degrees. This is below that at which iron melts, and we know that iron vapour exists high up in the sun's atmosphere. The matter was taken into consideration on the other side of the Atlantic by Ericsson in 1871. He attempted to re-establish the shaken credit of Newton's principle, and arrived by its means at a temperature of 4,000,000 degrees Fahrenheit. Subsequently, an underrated computation, based upon observation of the quantity of heat received by his sun motor, gave him 3,000,000 degrees. And the result, as he insisted, followed inevitably from the principle that the temperature produced by radiant heat is proportional to its density, or inversely as its diffusion. The principle, however, is demonstrably unsound. In 1876, the sun's temperature was proposed as the subject of a prize by the Paris Academy of Sciences, but although the essay of M. Jules Viol was crowned, the problem was declared to remain unsolved. Viol, who adhered to Dulong and Petit's formula, arrived at an effective temperature of 1,500 degrees centigrade, but considered that it might actually reach 2,500 degrees centigrade if the emissive power of the photospheric clouds fell far short, as seemed probable, of the lamp black standard. Experiments made in April and May 1881 giving a somewhat higher result, he raised this figure to 3,000 degrees centigrade. Appraisements so outrageously discordant as those of Waterston, Secchi, and Ericsson on the one hand, and those of the French savants on the other, served only to show that all were based upon a vicious principle. Professor F. Rossetti, accordingly, of the Paduan University, at last perceived the necessity for getting out of the groove of laws, plainly in contradiction with facts. The temperature, for instance, of the oxyhydrogen flame was fixed by Bunsen at 2,800 degrees centigrade, an estimate certainly not very far from the truth. But if the two systems of measurement applied to the sun be used to determine the heat of a solid body rendered incandescent in this flame, it comes out, by Newton's mode of calculation, 45,000 degrees centigrade. By Dulong and Petit's, 870 degrees centigrade. Both, then, are justly discarded, the first as convicted of exaggeration, the second of undervaluation. The formula substituted by Rossetti in 1878 was tested successfully up to 2000° centigrade; but since, like its predecessors, it was a purely empirical rule, guaranteed by no principle, and hence not to be trusted out of sight, it was, like them, liable to break down at still higher elevations. Radiation, by this new prescription, increases as the square of the absolute temperature, that is, of the number of degrees counted from the absolute zero of -273° centigrade. Its employment gave for the sun's radiating surface an effective temperature of 20,380° centigrade, including a supposed loss of one half in the solar atmosphere, and setting a probable deficiency in emission, as compared with lampblack, against a probable mutual reinforcement of superposed strata, Professor Rossetti considered effective as nearly equivalent to actual temperature. A law of cooling, proposed by M. Stephan at Vienna in 1879, was shown by Boltzmann many years later to have a certain theoretical validity. It is that emission grows as the fourth power of absolute temperature. Hence the temperature of the photosphere would be proportional to the square root of its heating effects at a distance, and appeared by Stephan's calculations from Viole's measures of solar radiative intensity to be just 6,000° centigrade, while M. H. Le Chatelier derives 7,600° from a formula conveying an intricate and unaccountable relation between the temperature of an incandescent body and the intensity of its red radiations. From a series of experiments carefully conducted at Daramona, Ireland, with a delicate thermal balance of the kind invented by Boys and designated a radio micrometer, Messrs. Wilson and Gray arrived in 1893, with the aid of Stephan's law, at a photospheric temperature of 7,400° centigrade, reduced by the first named investigator in 1901 to 6,590°. Dr. Paschen of Hanover, on the other hand, ascribed to the sun a temperature of 5,000° from comparisons between solar radiative intensity and that of glowing platinum; while F. W. Very showed in 1895 that a minimum value of 20,000° centigrade for the same datum resulted from Paschen's formula connecting temperature with the position of maximum spectral energy. A new line of inquiry was struck out by Zöllner in 1870. Instead of tracking the solar radiations backward with the dubious guide of empirical formulae, he investigated their intensity at their source. He showed that, taking prominences to be simple effects of the escape of powerfully compressed gases, it was possible, from the known mechanical laws of heat and gaseous constitution, to deduce minimum values for the temperatures prevailing in the area of their development. These came out 27,700° centigrade for the strata lying immediately above, and 68,400° centigrade for the strata lying immediately below the photosphere, the former being regarded as the region into which, and the latter as the region from which, the eruptions took place. In this calculation no prominences exceeding 40,000 miles (1.5 minutes) in height were included; but in 1884 G. A. Hearn of Colmar, having regard to the enormous velocities of projection observed in the interim, fixed 2,000,000° centigrade as the lowest internal temperature by which they could be accounted for, although admitting the photospheric condensations to be incompatible with a higher external temperature than 50,000° to 100,000° centigrade. This method of going straight to the sun itself, observing what goes on there, and inferring conditions, has much to recommend it; but its profitable use demands knowledge we are still very far from possessing. We are quite ignorant, for instance, of the actual circumstances attending the birth of the solar flames. The assumption that they are nothing but phenomena of elasticity is a purely gratuitous one. Spectroscopic indications again give hope of eventually affording a fixed point of comparison with terrestrial heat sources, but their interpretation is still beset with uncertainties. Nor can indeed the expression of transcendental temperatures in degrees of impossible thermometers be at the best other than a futile attempt to convey notions respecting a state of things altogether outside the range of our experience. A more tangible as well as a less disputable proof of solar radiative intensity than any mere estimates of temperature was provided in some experiments made by Professor Langley in 1878. Using means of unquestioned validity, he found the sun's disk to radiate 87 times as much heat and 5,300 times as much light as an equal area of metal in a Bessemer converter after the air blast had continued about 20 minutes. The brilliancy of the incandescent steel, nevertheless, was so blinding that melted iron flowing in a dazzling white-hot stream into the crucible showed deep brown by comparison, presenting a contrast like that of dark coffee poured into a white cup. Its temperature was estimated not quite securely at about 2,000 degrees centigrade, and no allowances were made in computing relative intensities for atmospheric ravages on sunlight, for the extra impediments to its passage presented by the smoke-laden air of Pittsburg, or for the obliquity of its incidence. Thus a very large balance of advantage lay on the side of the metal. A further element of uncertainty in estimating the intrinsic strength of the sun's rays has still to be considered. From the time that his disk first began to be studied with the telescope, it was perceived to be less brilliant near the edges. Lucas Valerius of the Lyncian Academy seems to have been the first to note this fact, which, strangely enough, was denied by Galileo in a letter to Prince Cesi of January 25, 1613. Father Scheiner, however, fully admitted it, and devoted some columns of his bulky tome to the attempt to find its appropriate explanation. In 1729, Bouguer measured with much accuracy the amount of this darkening, and from his data Laplace, adopting a principle of emission now known to be erroneous, concluded that the sun loses 11/12 of his light through absorption in his own atmosphere. The real existence of this atmosphere, which is totally distinct from the beds of ignited vapours producing the Fraunhofer lines, is not open to doubt, although its nature is still a matter of conjecture. The separate effects of its action on luminous, thermal, and chemical rays were carefully studied by Father Secchi, who in 1870 inferred the total absorption to be 88/100 of all radiations taken together, and added the important observation that the light from the limb is no longer white but reddish brown. Absorptive effects were thus seen to be unequally distributed, and they could evidently be studied to advantage only by taking the various rays of the spectrum separately, and finding out how much each had suffered in transmission. This was done by H. C. Vogel in 1877. Using a polarizing photometer, he found that only 13% of the violet rays escape at the edge of the solar disk, 16 of the blue and green, 25 of the yellow, and 30% of the red. Midway between center and limb, 88.7 of violet light and 96.7 of red penetrate the absorbing envelope, the abolition of which would increase the intensity of the sun's visible spectrum above 2½ times in the most, and 1½ times in the least refrangible parts. The nucleus of a small spot was ascertained to be of the same luminous intensity as a portion of the unbroken surface about 2½ minutes from the limb. These experiments having been made during a spot minimum, when there is reason to think that absorption is below its average strength, Vogel suggested their repetition at a time of greater activity. They were extended to the heat rays by Edwin B. Frost. Detailed inquiries made at Potsdam in 1892 went to show that, were the sun's atmosphere removed, his thermal power as regards ourselves would be increased 1.7 times. They established, too, the practical uniformity in radiation of all parts of his disk. A confirmatory result was obtained about the same time by Wilson and Rambaud, who found that the unveiled sun would be 1½ times hotter than the actual sun. Professor Langley, now of Washington, gave to measures of the kind a refinement previously undreamt of. Reliable determinations of the energy of the individual spectral rays were, for the first time, rendered possible by his invention of the bolometer in 1880. This exquisitely sensitive instrument affords the means of measuring heat, not directly like the thermopile, but in its effects upon the conduction of electricity. It represents, in the phrase of the inventor, the finger laid upon the throttle valve of a steam engine. A minute force becomes the modulator of a much greater force, and thus from imperceptible becomes conspicuous. By locally raising the temperature of an inconceivably fine strip of platinum, serving as the conducting wire in a circuit, the flow of electricity is impeded at that point, and the included galvanometer records a disturbance of the electrical flow. Amounts of heat were thus detected in less than 10 seconds, which, expended during 1,000 years on the melting of a kilogramme of ice, would leave a part of the work still undone; and further improvements rendered this marvellous instrument capable of thrilling to changes of temperature falling short of 1/10,000,000th of a degree centigrade. The heat contained in the diffraction spectrum is, with equal dispersions, barely 1/10th of that in the prismatic spectrum. It had accordingly never previously been found possible to measure it in detail, that is, ray by ray; but it is only from the diffraction or normal spectrum that any true idea can be gained as to the real distribution of energy among the various constituents, visible and invisible, of a sunbeam. The effective passage through a prism is to crowd together the red rays very much more than the blue. To this prismatic distortion was owing the establishment of a pseudo maximum of heat in the infra red, which disappeared when the natural arrangement by wave length was allowed free play. Langley's bolometer has shown that the hottest part of the normal spectrum virtually coincides with its most luminous part, both lying in the orange, close to the D line. Thus the last shred of evidence in favour of the threefold division of solar radiations vanished, and it became obvious that the varying effects, thermal, luminous, or chemical, produced by them are due not to any distinction of quality in themselves, but to the different properties of the substances they impinge upon. They are simply bearers of energy, conveyed in shorter or longer vibrations, the result in each separate case depending upon the capacity of the material particles meeting them for taking up those shorter or longer vibrations and turning them variously to account in their inner economy. A long series of experiments at Allegheny was completed in the summer of 1881 on the crest of Mount Whitney in the Sierra Nevada. Here, at an elevation of 14,887 feet, in the driest and purest air perhaps in the world, atmospheric absorptive inroads become less sensible, and the indications of the bolometer consequently surer and stronger. An enormous expansion was at once given to the invisible region in the solar spectrum below the red. Captain Abney had got chemical effects from undulations 12/10,000ths of a millimetre in length. These were the longest recognized as, or indeed believed on theoretical grounds to be capable of existing. Professor Langley now got heating effects from rays of above twice that wave length, his delicate thread of platinum groping its way down nearly to 30/10,000ths of a millimetre, or 3 microns. The known extent of the solar spectrum was thus at once more than doubled. Its visible portion covers a range of about 1 octave. Bolometric indications already in 1884 comprised between 3 and 4. The great importance of the newly explored region appears from the fact that 3/4 of the entire energy of sunlight reside in the infrared, while scarcely more than 1/100th part of that amount is found in the better known ultraviolet space. These curious facts were reinforced in 1886 by further particulars learned with the help of rock salt lenses and prisms, glass being impervious to very slow as to very rapid vibrations. Traces were thus detected of solar heat distributed into bands of transmission alternating with bands of atmospheric absorption far beyond the measurable limit of 5.3 microns. In 1894, Langley described at the Oxford meeting of the British Association his new bolographic researches, in which the sensitive plate was substituted for the eye in recording deflections of the galvanometer responding to variations of invisible heat. Finally, in 1901, he embodied in a splendid map of the infrared spectrum 740 absorption lines of determinate wave-lengths ranging from 0.76 to 5.3 microns. Their chemical origin, indeed, remains almost entirely unknown, no extensive investigations having yet been undertaken of the slower vibrations distinctive of particular substances; but there is evidence that 7 of the 9 great bands crossing the new spectrum, as Langley calls it, are telluric and subject to seasonal change. Here, then, he thought, might eventually be found a sure standing ground for vitally important previsions of famines, droughts, and bonanza crops. Atmospheric absorption had never before been studied with such precision as it was by Langley on Mount Whitney. Aided by simultaneous observations from Lone Pine at the foot of the Sierra, he was able to calculate the intensity belonging to each ray before entering the earth's gaseous envelope; in other words, to construct an extra-atmospheric curve of energy in the spectrum. The result showed that the blue end suffered far more than the red, absorption varying inversely as wave-length. This property of stopping predominantly the quicker vibrations is shared, as both Vogel and Langley have conclusively shown, by the solar atmosphere. The effect of this double absorption is as if 2 plates of reddish glass were interposed between us and the sun, the withdrawal of which would leave his orb not only 3 or 4 times more brilliant, but in colour distinctly greenish blue. The fact of the uncovered sun being blue has an important bearing upon the question of his temperature, to afford a somewhat more secure answer to which was the ultimate object of Professor Langley's persevering researches; for it is well known that as bodies grow hotter, the proportionate representation in their spectra of the more refrangible rays becomes greater. The lowest stage of incandescence is the familiar one of red heat. As it gains intensity, the quicker vibrations come in, and an optical balance of sensation is established at white heat. The final term of blue heat, as we now know, is attained by the photosphere. On this ground alone, then, of the large original preponderance of blue light, we must raise our estimate of solar heat, and actual measurements show the same upward tendency. Until quite lately, Pouillet's figure of 1.7 calories per minute per square centimetre of terrestrial surface was the received value for the solar constant. Forbes had, it is true, got 2.85 from observations on the Fall Horn in 1842, but they failed to obtain the confidence they merited. Pouillet's result was not definitely superseded until Viol, from actinometrical measures at the summit and base of Mont Blanc in 1875, computed the intensity of solar radiation at 2.54, and Crova, about the same time, at Montpellier, showed it to be above 2 calories. Langley went still higher. Working out the results of the Mount Whitney expedition, he was led to conclude atmospheric absorption to be fully twice as effective as had hitherto been supposed. Scarcely 60%, in fact, of those solar radiations which strike perpendicularly through a seemingly translucent sky were estimated to attain the sea level. The rest are reflected, dispersed, or absorbed. This discovery involved a large addition to the original supply so mercilessly cut down in transmission, and the solar constant rose at once to 3 calories. Nor did the rise stop there. M. Savelieff deduced for it a value of 3.47 from actinometrical observations made at Kiev in 1890, and Knut Ångström, taking account of the arrestive power of carbonic acid, inferred enormous atmospheric absorption and a solar constant of 4 calories. In other words, the sun's heat, reaching the outskirts of our atmosphere, is capable of doing, without cessation, the work of an engine of 4 horsepower for each square yard of the earth's surface. Thus modern inquiries tend to render more and more evident the vastness of the thermal stores contained in the great central reservoir of our system, while bringing into fair agreement the estimates of its probable temperature. This is in great measure due to the acquisition of a workable formula by which to connect temperature with radiation. Stephan's rule of a fourth power relation, if not actually a law of nature, is a colorable imitation of one, and its employment has afforded a practical certainty that the sun's temperature, so far as it is definable, neither exceeds 12,000 degrees centigrade nor falls short of 6,500 degrees centigrade. End of Chapter 5.